waves on vibration vibrated on strings and pipes. So for a first case, let's talk about strings. Now when a string is plucked, the first thing we observe is there will be a loop, a single loop produced. So there will be a top and there will be the one at the bottom. So at this point in time, we have points where there are vibrations and points where there are no vibrations. Like we know, this point here, where there is no movement of the particles, is called your node. While here is your antinode. So here we have a node too. Now for this first loop or waveform, we'll find out that the length is going to be measured from here to here. So from here to here is our L. Then we can get the wavelength of this waveform. Now, like we know, wavelength, which is lambda, is usually distance between two consecutive crests or trough. But in this case, we are making use of a standing wave or stationary wave, so we have to define wavelength in terms of nodes and antinodes. Now, for one wavelength, we need one complete oscillation. So for one complete oscillation, we are going to measure from here to here. So from here to here, it's not up to one oscillation. Because it's either we are using the one at the below wave loop or the one above. So if we are using the one above, from here to here is a semicircle, it's not up to one cycle. So we'll call this half wavelength or half lambda. So 1/2 lambda. So in this case, our L is equal to 1/2 lambda for a single waveform. Now, if we are looking for the frequency of this waveform, recall that our formula for velocity is V equals to F lambda. So frequency will now be V over lambda. So what did we get here? We said that the length of this string is equal to 1/2 of the wavelength, according to what we saw here. So if you make your lambda straight of formula, your lambda will be what now? To be 2L. So if we come back here, we substitute the value for our lambda, which is 2L here. So the frequency we are going to get to be V over 2L. Now this frequency, which is the frequency we get from the first vibration of a string, is called the fundamental frequency, F0. So it's called your fundamental frequency. So the fundamental frequency is the frequency attained when the vibration is just once, when you pluck or this string is disturbed once. So that frequency that will produce that vibration is called the fundamental frequency and is given by V over 2L. But the 2L is the length of the string. Because from what we got here, we saw that the wavelength is equal to 2 times the length. Now, this first frequency, called the fundamental frequency, is the strongest or the first possible frequency that you get from the vibration of a string. So we can have other frequencies. So that is now going to give rise to terms like harmonics and overtones. So what these terms are is just a way of explaining the next and the higher frequencies. Now harmonics are whole numbers or integral values of the fundamental frequencies, while overtones are multiples of the harmonics. So what we are saying now, for example, is if the first frequency is F0, we can have second frequency, the third, the fourth, and so on and so forth. Now these other frequencies, knowing that this is the first frequency, which is the first harmonics or the fundamental frequencies, from this place, from here to infinity, are called multiples of the first frequency or the fundamental frequencies, or we can say they are multiples of the harmonics. Now this F0 is the first harmonics or the fundamental frequency. So from this place, we can be calling them the overtones. So the second frequency is called the first overtone. This is now the second overtone. But this is the first harmonics, second harmonics, third harmonics. But in terms of overtones, this will be our first overtone. This will be our second overtone, third overtone. Because your overtones are multiples of the fundamental frequency. So here we have whole number. You know, this place is just 1. 1. But multiples of this first one are called the overtones. So multiple of 1 may be 2 times 1. We have this. 3 times 1 is just a multiple. We are multiplying the first frequency by some values. Now, if we are going to look for the second harmonics or the first overtone, the waveform will have to be 2 because the vibration will now be twice. So let's see what we have. We have something like this. We have the first loop. You know, these are string. So we have the first vibration and second vibration. Now, since it's a stationary wave, it has to form a complete loop like this. So this is the second vibration we are going to get. The first and the second put together. So from here to here is still the length of the string. Here to here is still the length of the string. So here now, we are now going to have series of nodes and antinodes. So we have node, we have node, and we have node. So we have antinodes and we have antinodes. I hope we call what are nodes and antinodes. A node is a point where there is no vibration or no movement. While antinode is a point where there is maximum vibration. So now we now have 1, 2, 3. 3 nodes. Now we said earlier that from here to here is half wavelength. So here to here is half wavelength. So 2 of them will make a complete wavelength. That is 1 full wavelength. We said that we're using the top to get our wavelength or we're using the bottom loop. So in that case, we can't use the 2 at once. So from here to here is half, here to here is half, which means the length of this string, that has been vibrated, when compared to the wavelength, they will be equal. Because from here to here is 1 wavelength. So if we are now going to get the frequency, using our formula for velocity of a wave, which is V equals to F lambda, our F again will still be V over lambda. Now in this case, what is our lambda? According to the comparison here, lambda is same as the length. So which means the second frequency now, so we've done the first frequency before, will be V over L. So that is for the second frequency, or what we call the second harmonics. Then in terms of overtone, this will be our first overtone. So we can get the next and the next. So at the end of the day, what we have now is this. We'll be having our frequencies. That is, the first frequency is, like we said before, was V over 2L. The second frequency is V over L. The third frequency will be what? If we increase these vibrations, this loop here, because we are talking of three vibrations now. So when we increase it, let's say we have something like this. So the wavelength, the length is now going to be from here to here. So the length is going to extend from here to here. So what will be the new wavelength? So from here to this place, we have node, 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 and node. Then we have antinodes. So you know we have 4 nodes, 3 antinodes. So the wavelength will now be half, half, half. So we have 1.5. So the length will now be 1.5 wavelength, which is same thing as 3 over 2 wavelength. So if you make your lambda the result of the formula, lambda will be 2L over 3. So which means for the third fundamental frequency, we'll be having 2L over 3. Okay, we are making use of the formula for velocity. So what we should have here is V over 2L over 3. So when you rearrange this, we should have 3F naught is, the 3 goes up, now be 3V over 2L. So now, if we put all of this in ratio, I mean something like this, the first F naught ratio, the second F naught ratio, the third F naught. So if we arrange them in ratios, which means the formula for the F naught will now be V over 2L ratio V over L ratio 3V over 2L. If we have all of them like this, then now we want to get just the values of the frequency. What do we now have? we divide through by V over L. So divide V over L. So this 3F0, this is the third fundamental frequency. After resolving here, we now got it up to this point. That's why I'm having it like this. So when we divide through by L over V. So we divide each of these by L over V. Find out that we now have V over 2L divided by L over V. Then we show V over L divided by. Okay, I think we'll continue from here. Welcome back. So as we were saying before, we are going to divide through by V over L. So when we do that, we are going to get values for our frequencies. So the first value for the fundamental frequency is V over 2L divided by V over L. Then the other one again, V over L divided by V over L. Then the third one is 3V over 2L divided by V over L. Right? So when we do that, we are going to have this and this will cancel out this. So this will cancel out this. And this will cancel out this. So we now have this at the end. So what do we have at the end now? We have 1 over 2 ratio. Here we have 1, then ratio 3 over 2. So since they are in ratio, we can remove them from fraction to whole numbers. So what do? We just multiply through by 2. So we'll multiply through by 2. Now have 1 ratio. So we'll multiply this part 1 over 2 by 2, 1 by 2, then 3 over 2 by 2. We'll multiply through by 2. We now have this will cancel this. We now have 1 ratio 2 ratio what? 3. So which means for a string, the frequencies are in order of this nature. So they are increasing consecutively. So from 1 to 2, from 2 to 3 to 4. So which means the fourth harmonics is going to be 4, the fifth to be 5, the sixth just like that. So they are just consecutive for a string. So we have their frequencies in this order. So which means our seventh harmonics will be our sixth overtone. So this is the order it goes. That is for a string. So now let's look at the one for a pipe. So let's go over to that now.